Hello everyone, I'm Don Mears. I am the oil and gas specialist for Thermo Fisher Scientific. I'm also an API certified training provider and teach a course on API Recommended Practice 578. Good news, we now have a third edition. And so what I'm going to talk to you about is all the changes and what it means to you in the third edition. Get ready, get excited, here it is. What we're going to cover and what you'll learn today is an overview of really what's in 578, third edition, and who and what and how it affects and some of the things that we changed during this documentation. We'll cover these in detail on these slides that you'll be able to refer to in the future. So get ready for positive material identification, material verification, and technologies that we're going to use throughout this presentation. What is API Recommended Practice 578 3rd edition? The title is Guidelines for Material Verification Programs for New and Existing, now listen to this, assets. Now, all of oil and gas, all of fabrication, all of the metals that are used in the oil and gas industry are considered assets. So what we want to do here with this material verification program is use positive material identification. We refer to that as PMI. And PMI is how we assess the material and that asset and the components of that asset. And we'll cover this with 578 and the different analyzers that have been used. And so it's very important that we minimize our corporate risk by following the guidelines of APIRP 578. Who and what are we going to talk about and how does it really affect? This is the good news. All of the oil and gas industries, all of the systems can apply this document. When you use the word asset, then the owner user can verify what that asset is. It could be a bolt, a nut, it could be a gasket, it could be a furnace, it could be anything. Because if it's functioning in the oil and gas industry, whether it's offshore, onshore, or midstream, upstream, and downstream, all of those sectors, it is what it covers. And so it covers what the owner user of that asset wants to be able to verify. So what did we do? What did we change from the second edition? And again, these editions go for at least 5 years. And we changed the title, Guidelines for Material Verification for New and Existing Assets. The older one was Material Verification for New and Existing Piping Systems. So taking that word out allows someone that has an asset in fabrication, for example, that's making a blowout preventer that's for the subsea, they don't have a piping system to really address. So that it's an asset, and that works very well. All sectors, as we said, currently cover this upstream, downstream, and midstream. And we really did a format in API in this document because I was like the vice chairman of this and been doing this for a long time. And we made these additions. One, refractory anchors are now covered and they never covered before. And we'll talk about that technology to be able to measure something small like an anchor. The other thing is XRF analyzers are updated as far as their detection capability with silica drift detectors. We refer to that as an SDD. This is a biggie here. There's a new technology called LIBS. The acronym means laser-induced breakdown spectroscopy. And that is added as well as an optical device like we've used before, optical emission spectroscopy. And so one really nice thing, it covers all statistical data with that and points that we put in NXA. It's excellent. And the really most important thing is the Chemical Safety Board came to our committee, and that's the federal government if you didn't know that. They came to our committee and said, we want to see more shall statements in your document. And so now we've added 4 shalls rather than should or may or must. They're shall statements. And you say, Don, what do you mean by shall? Well, the terminology is really explained in the document. Shall denotes the minimum required order to confirm with what it says. I like to say shall means you have to do it. It is a must. okay? A should denotes the recommendation, basic. You could or could not. A may, possibility, may or may not. A can is really a statement that is a probability. So shall means you've got to do it. So where is the first shall? The very first shall is in the general statement of material verification program, and that is an MVP. And notice this, it says this in the document: the owner user shall, listen to that, that's a must, shall establish a written verification program for all types of positive material identification, and during what? Construction of new assets. Okay, retroactive of existing assets. And then it shalls during all your maintenance, your repair, your alteration of all these assets. You are required to do a written document verifying this. Users that have high-risk systems, it's really mandatory. You know, if we have things like water going through the pipe, that's not a real high risk, but boy, you have hydrocarbons going through a pipe, and you have a leak, you have a blowout, you have a fire, you have deaths. We don't want that. And that's why this is so important to make sure that we have shall statements. And that's why the federal government and the Chemical Safety Board, OSHA, requested that we did it, and we did it, okay? So if we look at considerations and concerns with these assets that are out there, one of the things, we have about 7 different areas in the document. One of the things that we really have problems with, and that's substitution of carbon steel systems in low alloy systems. So low alloys have carbon steel, but it has chrome and moly in it, okay? And they all look alike. They look the same, but they're not. Another is substitution for carbon steel in general. And then stainless steels. Where we have stainless steels, you sometimes have ferrous and high temperature, and you have monels with high nickel in it, and monel and copper in it. So those get mixed up a lot, and when they do, it creates a problem. In HF alkylation plants, we have carbon steels, and you have hydrofluoric acid going through it, and sometimes the residual elements, we'll talk about those, really create a problem with corrosion. Big corrosion problems in all of these plants where you have hydrocarbons going through it is where sulfur comes in. It's called sulfidization. I'll explain that in the units of sulfidation corrosion. Gaskets are there, refractory anchors, we cover all of that. So what about these carbon steel substitutions, low alloy steels? They all look the same, but if you don't check it to see it has 1 1/4 chrome, half moly, and 5 chrome, 9 chrome, you don't check that, it's not going to do a good job for you, because high temperature and flow creates corrosion, and that corrosion and just ferrous materials can be very, very bad, and we check that all the time. And positive material identification technology can do a great job on that. The thing we talked about, considerations and concerns, is alloy substitutions in carbon steel. Where we have that HF acid, we have sulfuric acid, we have H2SO4, which is a sulfuric acid. And anytime a hydrogen cyanide's in there, you've got to really make sure you have the right substitutions of alloys in there and not just use carbon steel. So we mentioned that in the document. The other thing that's mentioned as a concern in this document is stainless steels and non-ferrous substitutions for high alloys. I use the word HF alkylation, so the alloy 400 has to be there. We have alloys like 304 stainless steel and 316, and 316 has molybdenum in it. We call it moly because molybdenum is very hard to say. So that has to be there, and if you don't test it and make sure 316 has the moly in it, then that can create a corrosion problem. So those are a wide variety of concerns. The biggest concern that we have is in HF alkylation units. There's another document that we have for that called API 751, and that's really corrosion problems based on residual elements. Residual elements are things that are left over in the heat and the pour of the metal, and like chrome plus nickel plus copper needs to be nominally 0.15% combined. But if you have one that is, say, 0.25% and one that's low, and you weld those together, you get corrosion right in that area. So Those are big concerns throughout our industry to minimize this corporate risk. The biggest problem that we've had in explosions in a refinery on the West Coast that was huge is what we call sulfidic corrosion. Sulfidic corrosion is that when you have carbon steel and you have hydrocarbons running through it, hydrogen-free or with sulfur in it, crude oil has it, so like crude units, and you don't have silicone in the pipe that it's going through needs to be at least 0.15%. If it's 0.1 and lower, you end up having an exponential corrosion, maybe 4 or 5 mils per year corrosion on that pipe. If you're not testing that, you should be doing it. And this is very important to be able to get that measurement out there and do a good job. So API RP 571 talks about that corrosion mechanism, but there's a whole document on sulfidic corrosion called 939C. So American Petroleum Institute 939C and 571 all covers that. And the big problem we had pre-1985 is A53 pipe had no spec for silicone in it. A106 pipe has a specification of a minimum of 0.15% in it. So we still have that 30 and 40 years ago, way out there, these pipes that are really corroding very fast. So that's a big one. Gasket materials are also something that, you have a pipe, you have a weld, and you have a flange, and then you've got a valve you're going to put to that. In between that is a gasket, right? So if you're not testing to make sure you have the right gasket material, you're going to have a corrosion mechanism. So that's all covered. API RP 578 covers anchors now in refractory. Now you think about it, these are what is welded inside a big vessel to put in a furnace, for example, fiber on it, or you put bricks to be able to have the insulation to get up to 1,000 degrees or 2,000 degrees, and they never tested them before, and so you get corrosion mechanisms for that. Now they could be small diameter, so new technology has a camera on it, and that is called XRF technology. You actually can zoom in at 3 millimeters and measure that small anchor, just like doing welds. The thing that the document issues are brought out in 578 is that PMI, positive material identification, should never be considered by many people in the past, in that they would trust MTRs, material test reports. But wherever that material came from, sometimes they didn't do the chemistry on it and they lied. So the document says MTR should not be considered a substitute for positive material identification. So we use the term, trust it, but verify it with positive material identification. So if I'm looking to all the roles and responsibilities of the personnel to carry out this positive material identification and have this written material verification program that we're talking about in the 3rd edition, it is very clear that it says there's several groups within an operating company. Could be a plant, could be a shop, could be a contractor, could be a vendor, could be a fabricator. So you look at all of that. And these departments that have to look at that to make sure it's the right material for the right process, vitally important so we don't have a fire and explosion. That is purchasing, engineering, warehousing, operations, reliability, QA, QC, inspection, and maintenance. That's a lot, isn't it? Well, we got to run it through everybody to make sure there's no mistakes. Many, many years ago, they decided to buy metal overseas, different countries. China particularly was one. And those mills didn't provide the material that they should. They would put the alloys in it and it would be out of spec. So we really now, and it was cheaper, yeah, we really now look at some of the steel mills in the United States and kind of press the issue that we really don't want damage, we want the correct material, and we can verify that. And so we have to examine this under construction and all our assets, and we need to do that in all locations and determine that by the owner user. So one thing we all have to have in our oil and gas systems is maintenance. And it's not going to last for the rest of our life. And by the way, this is where another shall statement comes up. The responsibility on your verification on your maintenance. And it says, it shall be the responsibility of the owner user to evaluate maintenance systems so that material verification can be designated and implemented and support mechanical integrity asset needs. Very strong statement under the shall. Now that's not only in maintenance, but turnarounds and all the assets. We have laydown yards for new construction. You've got to check it. Now, besides an element of maintenance, 578 goes on and talks about material verification. And that can be associated with receiving it in a warehouse, for example. It could be on site or it could be out there at a vendor's. And sometimes the owner users just send an inspection company out to where the vendor is and ask them to do all of this. But really it's to be able to check it before it comes to the field to be installed is probably a cost-saving benefits. And at the fabrication shop, they check it. And I teach on API RP 578 for the American Petroleum Institute, and fabrication people do come to my courses to be able to learn how to do this properly. Not just if you're working at Exxon or Shell or Chevron, but you're an inspection company and you come and take that course because it's important to understand how it is a quality assurance practice. So in these maintenance activities that we're talking about, one of the things is you have a temporary removal of a spool piece that's mentioned. You got to tag it, mark it, and do PMI. And there's an example of a spool piece put in the wrong location. It was carbon steel and it should have had chrome moly in it and exploded and blew up. Didn't even last 3,000 hours, man. That's no time at all. Well, are you doing that with the maintenance activity? Replacement of small bore piping is called there with threaded nipples and plugs and all of that. You know, it's one thing to have a pipe that's the right material, then on the bottom you have a plug and a nipple that goes in that plug and it's the wrong material and it corrodes away very quickly. Any replacement welds that you had in valves, sometimes in turnarounds, they put a weld around a valve, but they forget to check to see what weld material's there and what valve material was used. Turnarounds are big things that happen in all of the oil and gas industry, whether it's offshore, whether it's inside a refinery or a chemical plant or any kind of activity, turnarounds, and they involve heat exchangers. Every plant has a heat exchangers. You know, a heat exchanger has coils in it, and when you pull those coils out for cleaning, 578 says, hey guys, you better go ahead and check it and make sure it's the right material, and it goes back in the correct heat exchanger. I was in a foreign country not long ago, driving down the road, and inside that plant, and there were coils of heat exchangers laying out all around. And I looked in the plant and I looked at the man and I said, hey, do y'all have that tagged and marked to make sure that that coil goes back? It could be B2 and B3 coils. Does it go in the right heat exchanger? They went, duh, no, we don't. Boy, that's a bad situation. API 586 also talks about that, and there's lots of improvements, and there's been tremendous amount of explosions and fatalities from the blowing up of heat exchangers because it's the wrong material. When a tower internals are replaced, you got to check it. Removal of blinds for easy access that are blank blinds, got to check them, you know? Now, how do I check them? What technology do I use? Well, we're covering 3 technologies in this document. XRF, it stands for X-ray fluorescence, probably used 90% in all of this work. There's a new technology that was added. I mentioned LIBS, laser-induced breakdown spectroscopy, and then the next one is optical emission spectroscopy. So we have XRF, LIBS, and OES, and they all are mentioned in the 578 document. What about that XRF analyzer? The best way it works is it sends out with a little tube. It kind of lights up and sends out an X-ray. Well, it affects the electrons in the inner shell of that atom and they get ejected. When it does, it sends back electrical magnetic energy into that analyzer, and it's little pulses, you know? And then that SDD, silica drift detector, converts that to kilo electron volts. Ooh, if you ever took chemistry, you might know what a KeV is. Maybe you don't. But anyway, it compares it to an onboard library and does the calculations and displays what's in that. It's non-destructive, doesn't make a mark on the pipe. It's very light, and it does light elements like silica, sulfur, phosphorus, magnesium, and aluminum. I mean, that's new technology, and it goes down to part per million levels. Boy, that's great stuff. That's why it's used more commonly. One thing about it, it's not intrinsically safe certified, so you may have to consider whether you need a hot work permit or not. The particular analyzer I'm talking about that I just mentioned is called the XL5 handheld XRF analyzer, and then the next one is called the XL2. Now this is Thermo Fisher Scientific, the market leader in handheld XRF analyzers. They're a 5-watt tube in the 5. It is the smallest, lightest, have 2 cameras on it. One, you can take a picture of the asset. 2, you can look in the camera and see where you're shooting it on the asset. Isn't that cool? You can collimate that thing from 8 millimeters down to 3. 3 millimeters, about the pin size of the hair on your head. Well, my hair is just about going away, but you know what I mean. It's very, very small. And one of the things is that you can, with that analyzer, download it, and you have the software to do that, filter reports, make reports, and it's unbelievable how great that analyzer is. You don't have one, you better contact your representative in Thermo Fisher Scientific and get one. It's the hottest thing on the market. Then the next thing they did is called an XL2 Plus, which is more rugged. Only has a 2-watt tube, and it is very good. It's really what I call splash proof and dust proof, and it has a camera in it as well. More rugged, more of that, but not quite as hot an analyzer like the XL5. The XL5 has filters on it, main filter, low filter, and light filter. That means it adjusts all of that voltage and current to be able to excite that electron in the K shell or the inner shell. Boy, it's good. You can see I'm excited about it. You need to consider an XL5 or an XL2. The next technology that we want to discuss that's in API RP 578, 3rd edition, is LIBS. Can you remember what LIBS stands for? Laser Induced Breakdown Spectroscopy. What does that really mean, and how does it work? What technology are you talking about, Don? Well, you actually have a handheld. And that handheld, when you pull the trigger, you have to actually seal that front part of the device on the metal, and you purge it with argon. The purge of the argon removes all the air and everything that's in there, oxygen, nitrogen, removed. And then we pulse out a high-intensity laser such that it totally ablates the metal. It melts it, dude. It does a great job of doing that, and when it does that, it gives off a color spectra. That color spectra can be measured, you know, and we call it, and this may be a little technical for you, lines in nanometers, right? It goes from 175 up to 410 nanometers. You can go higher than that. Visible light, like in a rainbow. Y'all have seen rainbows, haven't you? The blues, the yellows, the green, all right? That's optically, I'm seeing it, right? Well, that's what's happening. Instead of visible, it's ultraviolet, and that's where we're moving. You know what's nice? It can measure carbon. Carbon comes out at 193 nanometers, and the key thing here about using an optical device with laser, especially, it's small, it's handheld. The argon bottle is real tiny. Real tiny. Oh yes, which we're going to cover in just a minute. It's a great big one. This one's a lot smaller. So you can get into tight spaces. You can measure carbon at L grade and H grade. That's a 0.03%. Boy, that's low. H grade, high carbon, is a 0.06, 0.08, right? In that range. That's very, very low concentrations. What does that mean? If I'm doing that in low concentrations, I've got to sample prep. If you don't sample prep, and that means clean the metal properly with a proper disc that you don't cross-contaminate, and you clean that properly, then you go ahead and get ready to shoot. But also, a little more different than XRF, you have to do an empirical calibration on these devices. That means you got to calibrate in the field on a standard with the material that you're measuring. XRF is great because it has fundamental parameters, and you can go from base metal of iron to copper to aluminum. Not so with this. You got to calibrate with each one, but that's the way optical devices are, and you get great results. You can qualify and quantify with this very easily, and we do it with a spectra, and we measure that spectra optically. those detectors that detect them, there's 3 in the LIBS devices that are out there. They have charge coupled devices, CCD detectors in them. So they do a great job. Sample prep's very important. The clean argon, I might mention this, argon has to be laboratory quality. You know what that means? 99.999%. You have any moisture in it, won't get good results. And buddy, you spend time trying to get low levels of carbon, you want to make sure it's right. One nice thing about this, Thermo Fisher Scientific makes a good LIBS device. It's unbelievable. They call it the Apollo. It's handheld. It is wonderful and it's recommended. It's a class 3B laser. It has the ability to detect carbon, and it can do low levels of carbon, and it depends on what you're doing. I'm doing carbon steel, a low alloy steel, I'm stainless steel. You still have to calibrate for all of that, and this can do a great job. It has a very compact geometry. That means it's very small, and it looks like that XL5 I was talking about, a little bigger. All right, with a tilt screen. You have the cameras that you had on the XRF. You have the micro and the macro. I get those words mixed up. But what that means is I can take a picture of my asset. And then where that asset I want to shoot, I can look and point that laser and help you point it. And you see how clean it is. And you pull that trigger and you can see what's going on with that pulse laser that's going on. It's smart and connected. That means I can download all of that. I can Bluetooth, I can USB, I can even use Wi-Fi, and go to all the software that it has to do your reports and make it very, very applicable to you. That application and interface is very, very easy. You want to look at that. That is referred to as the Apollo. The next device I wanted to talk about is the optical device. It's called OES, Optical Emission Spectroscopy. Now this has been out on the market for a long time. It's been used dramatically. And one of the things about that device is that when you sample prep that and you shoot it out, it's an electrical discharge. So inside the handheld portion, you have a probe that sticks out. It's called an electrode. It's sharpened, it's made out of tungsten. Discharges electricity, and that electricity ablates the metal. It measures carbon too. Both the LIBS device and this device can do low levels of carbon. We're talking about L grade and H grade. That's very, low levels, 0.03 and lower percent. H grade is a 0.04 to a 0.08. That's very low levels of carbon, and it does a great job for it. Now, the disadvantage of the working principle of the OES is it's a great big box. You have to have it on a big carrying cart. The argon bottle is very tall, and the handheld is not all that light, and it's electricity. So hot work permits are required. You can't work in bad weather like rain. You can't stand in the rain and use an OES. You're going to get electrocuted, right? So it's a thing that requires good technical experience. You got to know your metals if you're using OES. The other thing, that burn chamber, you have to clean constantly. You're going to have to purge the argon out. This is optics. OES requires, and LIBS, that the instrument warm up and stabilize. XRF, on the other hand, cools down. That detector on XRF actually is minus 27 degrees centigrade. This warms up. So you really need some expertise and capability to use these devices to let them do the job that they want to do. Okay, now we're going to talk about some common questions that people ask regarding this seminar. And the very first one that came up was, why did the guidelines change in API RP 578? What a lot of people really don't realize is that within the American Petroleum Institute, whether they do a recommended practice or a standard, we always go over a 5-year period for each one and make revisions. Why? Things change. I mean, technology changes, enforcement of OSHA and regulations changing, the chemical safety boards making changes. So we in API that have offices all over the world, right? We have them all over the world, have to make those changes. So that is our charge. If you don't realize that, then you're not getting up. Example, the second edition of 578 didn't even mention LIBS because it wasn't out. Now it's in. Didn't mention any of those things we talked about, anchors, measuring those. Yeah, change, okay? Change in other documents, change in technology, change in enforcement. That's why we have guideline changes every 5 years. And we as a committee have to work through that. And normally it takes about 2 to 3 years to do the rewrite and vote on it and ballot on that and get approval by all the owner-user operators. Another common question that we come up with is, how do I determine what technology is best for me to perform positive material identification? Well, the easiest answer I know, so we've covered XRF, LIBS, and OES, right? Those are the 3 technologies, right? The very first thing you would ask is, do I need carbon analysis in my PMI? Do I need to know how much carbon's in there? If the answer is yes, then you're not going to use XRF because it can't do carbon, right? So that's going to be the choice of LIBS or OES. And obviously I talked about OES being great big card and heavy and older technology. You want to look for that Apollo that I talked about, the laser-induced breakdown spectroscopy that Thermo Fisher puts out. Look at that. That's handheld, newest technology, and it works very well for carbon. Now, if I don't need carbon, the most common technology that you're going to use is XRF. Probably 80% of the PMI, maybe as high as 90 in some cases, of the positive material identification out there is all XRF. So what is it I need to measure? What elements do I need to know? Would help you decide what technology you want to use for that application. Another real common question that comes up is, can you please explain to me what sulfidization means? I get that all over the world, no matter where I am. What in the world are we talking about? Do you remember the document I talked about earlier? The document is API 939C, and we referred to the fact that that is sulfidization. What that means is, if you have a metal pipe, you have a vessel, and you're high temperaturing crude oil, for example, hydrocarbons, right? And you're raising that temperature, all of the hydrocarbons that we've got could have hydrogen in it, without hydrogen. It has sulfur in it. A lot of sulfur, actually. And as it goes through that pipe at elevated temperature, right, that sulfur can leach out on the inside of that pipe or that vessel, and that sulfur can be attached to the walls. And that's like coating almost, right? It's called sulfidization. Sulfur being impacted on the pipe, the vessel, the walls, or whatever's there. So what we have in the API 939C is, boy, you get a large amount of it according to 939C if you don't have silicone in the carbon steel. Remember, it had to be 0.1% and higher. If you don't have that, then you're going to have a lot of accumulation. And it is a big problem in all of the oil and gas, and we need to be aware of that. The very last question that I think is most common that many people give is, how does one really start to develop a material verification program? I mean, what's the beginning steps here is what people really ask. Well, if I go to an owner-user, you have all the different work groups within owner-user's facility. You've got your inspection group, your QA/QC, you have your engineering group, your project engineers. They normally pull together a committee to work through this issue. If you had an older MVP, according to 578 3rd edition, you shall, owner-user, develop a new one. All right, you've got to do that. Well, that development would be, go back and see what we did before. And every material verification program looks at the assets. Is it new or is it existing? The existing assets is a longer, tougher thing to do because you have to shut down the plant, you have turnaround activities, you've got lay down and maintenance repairs and lay down yards. All of that has to go in conjunction with the way I'm running this plant. But I've got a new one, you know, I have a contractor out there and he's got a laydown yard and he's building vessels and pipes and putting in valves. That's an easier situation for material verification. The main thing that we want to get across to you on that material verification, get your group together of all these departments and start, itemizing each area, what technology you need to use. If you need carbon, you ought to pull in the LIBS in it to it. rather than OES. Pull that LIBS in there. XRF is the main, and that's what you're using throughout. What kind of reports do you need? How qualified does this inspector have to be? You put qualifications so that that inspector that's working that normally is a contractor, right? And you all know that you've got to have a list of what you want him to do each day with that instrument. One of the best things as a QA/QC is that instrument calibrated properly? Is he going to use it properly? And the results that I'm getting back, can I trust those results? So those are really beginning steps, and I think we gave you some ideas in the API document that you've got to do that and keep versions of it and keep moving forward with it. So I'd say move forward, and that's the best I would suggest to you. Hey everyone, we're coming to a conclusion here. I want to thank you for watching and staying plugged in. I want you to know API RP 578 3rd edition is something you're interested in. Thank you.
To learn more, visit us online at thermofisher.com.